So let's talk about Diophantine equations, Pythagorean triples, and incremental research. So there are different types of research that someone can do. In an academic setting, we have the idea of basic research, and basic research focuses on the idea of expanding human knowledge about some discipline or about a particular topic. It looks for a fundamental understanding of that discipline or that particular idea. The focus is on theory, the how, and the why, and not really concerned with other aspects beyond the idea of just learning more about something. Now, that often leads to an application or application areas. And in academic research, there's also applied research, which focuses on solving specific problems. So there's some particular thing that needs to be done. And in an academic setting, that often overlaps considerably with the basic research and the applied research aspect, expanding knowledge, fundamental understanding of something, and using that to solve a particular task, solve a particular problem. And then in the application sense, the use of the result is the important component. In basic research, how you're going to use something isn't as important as being able to fully understand the thing. So in a non-academic setting, in industrial or business settings, then the research corresponds to like the research and development idea, where again, it's very closely related to the applied academic approach of solving a specific problem and using that solution in a very specific way. Again, there are certain businesses and industrial settings that do basic research as well to expand knowledge, but usually the industrial or business setting is developing a product for sale ultimately. So the different sense, the basic research is sometimes called pure research or fundamental research, and they don't always fit neatly into these separate categories. There again can be business settings that do business research and do basic research, which ultimately sometimes the basic research feeds back into the business purpose and sometimes it doesn't. But basically there are these big broad generalizations of different types of research. And so what we're going to look at are some ideas related to the basic academic research approach. And in this basic research, there are two kind of potential approaches we can have to doing basic research. One is problem-based. Now, we said that we don't care about specific problems or particular applications, but there are still problems like we've seen earlier in problem-solving settings. Here's a problem we want to solve. How do we solve this problem? We don't necessarily worry about it having a general use beyond just fundamental understanding of something. But we start with the problem and we learn or develop the necessary tools to solve that problem. And so basic research in an academic setting can proceed in that direction. Here's a particular problem someone asked or that we came across, and we want to try to answer that problem. So we determine all the tools, we apply the problem-solving strategies, the 4 steps from Polya, and we look at how to solve that particular problem. There's another approach called an incremental approach. And this one starts off even more basic. We begin with something that we know, some knowledge base, and slightly modify one aspect of something. We learn its effect, and we figure out what happens when that thing gets changed, and then we repeat the process. We change that thing again a little bit more, or we change something else, and very slowly making modifications, exploring the meaning, the result of those modifications. So in the 4 steps from Polya, this corresponds to the final stage when we said we're going to look back and around to see where else this applies. We're going to look around by saying, if I change this, what happens? If I change this thing, what happens? Change one small thing at a time. And very quickly we can go from a knowledge base of things that we all agree on, we all understand, we all believe, or whatever, and by making minor changes, we can quickly get into areas that are beyond what we already know. So we're going to do this with the idea of Diophantine equations, which are just equations involving integer coefficients and integer solutions. Now, sometimes the coefficients are fractions, but we can turn that into integer coefficients in an algebraic equation, multiplying by the common denominator and so on to get rid of the fraction. So occasionally we'll see things that have fractional coefficients in equations, but the key point is the solutions we're looking for. We're looking for integer solutions. And since Diophantine equations are named after the Greek mathematician Diophantus, we're usually looking for positive integer solutions. I said since it's named after Diophantus, in ancient Greek mathematics, zero and negative numbers were not part of the traditional mathematical setting. They were part of business settings. Okay, someone owes someone money. They understood that context. Okay, you've paid them off. They understood that context. But that wasn't mathematics. That was business setting. That was not for this high-minded mathematical approach to things. So they were dealing only with positive values. Diophantus probably lived in the 3rd century. There are some ambiguities and some unclear things of when he actually lived. Not much is known about him personally, just the results of some books that he wrote. In particular, Arithmetica. Only 10 of the 13 books have survived in different pieces. There's some Greek portions and some part of it in Arabic. And the reason that they know there are other books are references to those other books from other sources. And so Diophantus wrote some other, several other pieces as well. Fragments of those exist, but the references, we know they were written, references to those in some places. Diophantus himself will say the proof of this result is in this other book. Go look there, this other book that I wrote, and we don't have all of those pieces. But again, probably around the 3rd century. Some people give him credit for inventing algebra, but the idea is not that. The idea is that he found particular problems and collected techniques and applied those techniques to a bunch of different problems. And so a lot of the problems in his books relate to kind of, some of them are mind teaser kind of things, brain teaser problems. Some are kind of the number puzzle things, and a variety of different problem types and then techniques. So one famous thing that's attributed to someone writing about Diophantus in the sense, here lies Diophantus, the wonder behold. Through art algebraic, the stone tells how old. God gave him his boyhood, 1/6 of his life, 1/12 more as youth, while whiskers grew rife. And then yet 1/7 ere marriage begun. In 5 years there came a bouncing new sun. Alas, the dear child of master and sage, after attaining half the measure of his father's life, chill fate took him. After consoling his fate by the science of numbers for 4 years, he ended his life. And the question is, how old was Diophantus when he died? So since the question is how old was he when he died, that's an integer solution that we're looking at. And there's all these pieces in place. And you see 1/12 and 1/7 and so on. So there are these fractional values, but that equation, there is an equation that you can pull out of this. And this equation corresponds to a solution which may have nothing at all to do with Diophantus. It could just be a completely made-up problem that just is a nice problem in terms of the calculation and the numbers working out and so on. So see if you can solve that problem. It's a fun exercise in trying to solve equations. So trying to understand the English and converting the English into equations and then solving those equations. Well, solving that equation, there's one equation. Now, Diophantus in his time didn't have the nice symbols and the notation that we have, and so I've seen some of the writing, and it's okay. So first of all, it's in Greek, but beyond that, the idea of the symbols themselves and what they how you write down a quadratic equation or how you write down something to a power. We're not going to worry about any of that. The idea that we care about is just the equations with these integer solutions. But it's nice to have this historical sense of what's going on. All right, so as an example of a Diophantine equation, let's begin with a very simple Diophantine equation. Let's just solve the equation a plus b equals c, where a, b, and c are all positive integers. We look at that, and we see that there are lots of solutions to a plus b equals c. And not only that, we can create solutions. So the question of how many solutions are there, well, there are infinitely many solutions. To find one of those solutions, all we need to do is pick an a, pick a b, make sure they're both positive integers, and then c will be another positive integer. We do have to be careful about the order we pick those, because if we pick a and c first, then we may have to pick a negative number for b, and we have this condition of all of them being positive integers. And so the idea is we can pick any a that we like, pick any b that we like, add those together, and that gives us c, which is a solution to this equation. So it's a very simple Diophantine equation, and really too simple to be interesting for us. Now, if we did not know how to add yet, then this would be a problem, this would be a task, this would be something that we could learn from. It wouldn't be a common knowledge base. But we're going to take this idea of a plus b equals c as a common knowledge base, and then we're going to make changes and see where that can lead us. So we're going to do an incremental adjustment, and the first incremental adjustment we're going to do is, let's make the condition, let's add the condition that not only are a, b, and c positive, but that a is less than b, which is less than c. Okay, so that doesn't make the problem any more complicated. We still pick our a, we pick our b, and we calculate the c. The only thing this does that the previous didn't do is, although we had different letters, different names, A, B, and C, A and B could have been the same value. Now we've added this condition that A and B can't be the same value. We just made the change to see what happens. Okay, so that does give a different set of solutions, still infinitely many solutions, and the process is still the same. It's just that when we choose A and B, we have an extra condition to pay attention to, something to be concerned about. So again, how many solutions and how do we find a solution? Same exact idea. That incremental adjustment changes things. It actually changes things in a major way, but not as dramatically as really requiring us to change anything other than just make sure that A and B are different at the beginning. So we could do a different incremental adjustment. What if instead of A less than B less than C, we said A greater than B greater than C? And when we look at this incremental adjustment, the question of how many solutions are there now, well, if A is bigger than B, that's fine. We can do that. We can choose an A that's bigger than B. But when you add these two numbers together, we're going, with them all being positive because that's a requirement, the answer is going to then be bigger than either A or B. So in this particular incremental adjustment, we end up with something that has no solutions at all. So as we're making these adjustments, sometimes it leads us to a new place where there's new answers or new expectations or new possibilities, and sometimes it leads us to places where there are no possibilities at all. as with this particular adjustment. But we could do other things. Instead of that, we could say, okay, let's change the operation. Instead of plus, let's use minus, or let's use multiplication, or let's use division if we wanted. We could use the modulus. We could use whatever operation we wanted, and leave the other pieces all the same, whatever condition we are, and then start making this one change and see what happens. We could also, instead of focusing on positive integers, we could allow negative values. We could, again, instead of saying greater than or less than strictly, we could have less than or equal to, or greater than or equal to. We can do all these incremental adjustments and see what happens to the equation, see what happens to our understanding of that particular situation. But then we could also do an exponential modification. And so for an exponential modification, the idea here is it's still actually an incremental change. Let's just throw an exponent on something. Let's square the a and see what happens. So a, b, and c are back to just being positive integers. We're not worrying about which is larger or which is smaller. We could add that condition if we like. But let's just solve the equation a squared plus b equals c. And again, we see that if we choose an a and choose a b, all we have to do is square the a, add it to b, and that gives us our answer c. We still have infinitely many solutions, and it's still easy to find a solution. Now, if we pick a different starting point rather than choosing a and b, then we may not get answers. With that particular c, there might not be an answer that corresponds to positive integers on the other pieces. So sometimes we would say, all right, how many solutions are there that have this output on the right-hand side? What do those solutions look like? Are there some right-hand sides that aren't possible in this situation? If a has to be squared and you're going to add b to that, are there some answers that you can't get as output? And so we can ask these kinds of questions from this kind of exponential modification. But as far as just solving the equation, there's not much difference from the previous settings. So what if we put the square on the b instead? Well, since there's no condition, no requirements between a and b, that's just kind of a renaming. You just call a b and call b a, and a plus b squared equals c corresponds to the same idea. Here you pick the a, you pick the b, you square whichever one that says to square, you add those together, and that gives you the c. But what if the squared term is on the right-hand side? Is that more difficult? So you think about what might happen. How could we find a solution to a plus b equals c squared? How many solutions are there? We can't just pick any a and b anymore that we want, because the answer we get might not be an integer squared. But at this point, we could think about, well, we could choose the c and one of the other values and make sure that the values are appropriate in a way that makes sure we avoid the negative values. And so we could see how to modify this. Not every choice of a and b will work for this equation, but we see that it's not much different than the other settings that we had so far. So what if we have two exponents? What if we have a squared plus b squared equals c? Is that any more complicated? Again, we pick the a, we pick the b, square the a, square the b, add them together, that gives you the c, and we see that that's not difficult either. We get a different c on the right-hand side than we did with the a and b to start with, but it's still the same exact procedure. What if we put this square, one square on the left-hand side, one square on the right-hand side? And again, we see that we have to think a little bit more, but the end result is no more complicated than anything we've had so far. But what if we make it more interesting and have exponents on all three pieces? So a squared plus b squared equals c squared. And the idea then is now there's some more work to do. So the question of how many solutions are there and how do we find a solution How many solutions are there to this? Well, if we think about a squared plus b squared equals c squared, that's familiar to us. That corresponds to the Pythagorean theorem that we all know and love. And so the idea there is we expect there's lots of solutions to these, but we don't probably know very many solutions off the top of our head, and we don't really have a good way to find these solutions. At least not yet. So these solutions to this equation, again with a, b, and c being positive, we're going to call these Pythagorean triples, again because of the connection to the Pythagorean theorem. And to keep with the theme, Pythagoras, another ancient Greek mathematician, but you've heard of Pythagoras, you probably had not heard of Diophantus. So we're going to write a triple as a tuple, just A, B, C. And so instead of worrying, we know if it's a Pythagorean triple that the things are squared and they're added together, and a squared plus b squared is going to equal c squared. So we'll just write down the triple, just the numbers themselves, the a, b, c portion, the solutions to that equation. And so some Pythagorean triples that you do remember probably from school days, 3, 4, 5. 3 squared plus 4 squared is equal to 5 squared. That's 9 plus 16 is 25. Another one is the 5, 12, 13 triangle that you may remember. And again, 5 squared plus 12 squared is 25 plus 144, which is 169. 169 is 13 squared. So 5, 12, 13 is another Pythagorean triple. So maybe take some time and see if you can find some other triples yourself. There are a lot of them, and there are a lot of things that don't work. So there are numbers that end up with these decimal portions or fractional portions and so on, or square roots of things that are even irrational numbers could be possible. And so the Pythagorean triples themselves have to be solutions to the equation where the a, b, and c are integers. All right, so now we have this equation. We're thinking about how we can maybe find some solutions, and we're going to explore these kinds of triples a little bit more. So if we have two triples, one thing we might want to do is compare those two triples. So if we have two triples, say ABC and DEF, let's say that we're going to write this triple ABC in increasing order. So A is less than or equal to B, is less than or equal to C. We're making these less than or equal to so that we can have the idea of equality between the pieces if we want that, and we don't have to have it, but we can have it if we want that, or if it's possible. There might be situations where that's not even possible, but we allow the possibility. All right, so if we have these two triples, ABC and DEF, then let's say that one of them is smaller than the other, so ABC is less than DEF if A is less than D. Right, so we're looking at just the smallest value of each one of these. And in this case, so the A is smaller than B, smaller than C, or at least less than or equal to. D is less than or equal to E, is less than or equal to F. And so we are looking at, we'll say this triple is less than this triple if the first value of one is smaller than the first value of the second one. All right, and then we'll say the less than or equal to is if A is less than or equal to D, then we'll say this first triple is less than or equal to the other. But let's think about this. We're saying something in this kind of trying to understand these like we understand numbers. We say, okay, we learned about numbers, and then we learned how to compare and say this number is bigger than that number. With counting numbers, that made sense because you had to add more to get there. With fractions, we took some time and we learned about how to compare two fractions and see, is this fraction bigger than that fraction? And we're trying to do the same thing with this new thing that we have come across, these Pythagorean triples. And so to see this idea, we had the 3, 4, 5 triple, and we had the 5, 12, 13 triple, and 3 is less than 5. So by this idea, we're saying that the 3, 4, 5 triple is less than the 5, 12, 13 triple. Now, does that mean anything? Is that valid? Is that legitimate? Well, let's see what the effect of this definition is. This effect of we're trying to use ideas that we're used to in a new context. And so we want to see whether this causes any problems at all. Now, with numbers, with regular numbers that we know about, whether they're integers or fractions or real numbers, if m is less than or equal to n, so we have these two numbers m and n. If m is less than or equal to n, and n is less than or equal to m, then those two numbers are the same. So if one number is less than or equal to the other one and it works the other way, the only way for this to happen with numbers is for these to be equal. And so that's really what we mean in terms of less than or equal to. And so let's say we have two triples, and let's call them A and D just to make it easier to keep track of them. So we have A, this triple A, which has whatever numbers A, B, C, and this triple D, which has these numbers D, E, F. There could be same numbers in some, even between them. The different letters mean they can be different. It doesn't mean they have to be different. So our question is, can we have this triple A being less than or equal to D, and the triple D being less than or equal to A, but not have the two triples be the same? So the idea here is we want to think about how we could have A being less than or equal to D and D being less than or equal to A, but then have these two values not being the same. So what I want you to do is to pause this video and then either create two triples that where the first one is less than the second one and the second one is less than or equal to the first one, but that the two are not the same, using our definition that we are trying to mimic the way numbers work. And so either create a pair of triples like this, where they're not the same, but this less than or equal to idea that we've created still holds, or come up with a convincing reason that there is no such example, that these Pythagorean triples work just like numbers. And if you can convince me of that, then fine. That would mean that this less than or equal to idea is valid. Otherwise, it would mean that we're going to have to change the less than or equal to in some way to make it more meaningful. And if we're going to use the symbol, we want it to make sense and work like the symbol does in other contexts. Otherwise, we either need to repair the symbol, come up with a better definition, or replace that symbol and use something in its place. So go ahead and pause the video and see what you can come up with. All right, so you find out that more care is needed. We do need to take some care with the values, because, for example, if we let A be the triple 12, 16, 20, and you can check that to make sure that is in fact a Pythagorean triple, and D be the pair 12, 35, 37, the only way that two triples can be less than or equal to each other is if the first value is the same. And in both of these, the first value is the same, so A is less than or equal to D, and D is less than or equal to A, but the other two values are not the same, and so the two triples are not equal to each other. So here's an example where the values the two triples have the conditions that we want. A is less than or equal to D and D is less than or equal to A, but the two triples aren't the same. You may have come up with a different triple. Hopefully you found something that works. If you came up with an argument for why one of them being less than or equal to the other and the other way around means they had to be the same, then you want to re-examine that argument and see where you must have gone wrong, because we do have at least this one example and lots of other possibilities as well where these two triples, by that definition, well, this one should be less than or equal to that one and the other one should be less than or equal to, so they should be the same, but they're not. Okay, so what do? Well, what happens is this incremental approach that we've tried here doesn't always lead to useful things. We can't just always use our common knowledge and say, okay, well, this is what this means. So we're going to have to adjust in some way. And so we could adjust in terms of either making a new definition for what less than or equal to means. Instead of just the first value, maybe we need to look at the second one and then the third one. So we can make a more detailed definition for this comparison. And there are other things that we could try as well. So a different direction that we're going to go, rather than rewriting that definition for less than or equal to just yet, is we're going to look at what we will call primitive Pythagorean triples. Now, we still may have to go back and rewrite the less than or equal to definition even after this, but this change may allow that definition to work. So we're going to make one change and then we'll come back and make a different change if we need to. We know what we want less than or equal to kind of do when we're comparing these two things, but we're not yet sure how to make that happen. Okay, so for primitive Pythagorean triples, we're going to call a triple primitive if the three numbers a, b, and c have no common factors other than 1. And if two numbers, they don't have to be prime numbers themselves, but if two numbers have no common factor other than 1, we call those two numbers relatively prime. We don't need to worry about that here. All we care about are that a, b, and c have no common factors other than 1. And if that happens, we will call that triple a primitive triple. So 3, 4, 5, 3 and 4 and 5, they don't have anything in common. That's a primitive triple. 5, 12, 13 is a primitive triple. The triple that we just saw, the 12, 16, 20, that's not primitive because all those numbers are even. And so the common factor there's a common factor of 2. And so that triple is not a primitive triple. In fact, in that particular case, there's a common factor of 4. But again, as soon as we find a common factor that's bigger than 1, then we know that that triple is not a primitive triple. All right, so the question now is, if we keep our definition the same for less than or equal to, and we have two primitive triples with a less than or equal to b and b less than or equal to a, in that case, then, is a equal to b? So we want to think about that, see if we can apply the same ideas from before, what happened in the previous example that we just discussed. One of those triples was definitely not primitive. The 12, 16, 20 triple is not primitive. So maybe we don't have to revise the definition of less than or equal to. If this works, then we can say, well, when we're comparing these using less than or equal to, we just want primitive triples in place. But if we can find two primitive triples where this one is less than or equal to the other and the other is less than or equal to the first one, but then the two triples are still not equal, then that means we would have to go back and revise the definition of less than or equal to. All right, so feel free to ask questions as usual in the comments, by email, or on Discord, and have a great day.